Hello everyone. Let us start today's session. This is session number 16 and we have already covered the characteristics of transmission line. Then we have covered the modeling of transmission line and in the subsequent classes we have seen the power flow in the transmission line. Now we have enough study to now to do we can do the power flow analysis in transmission line. So therefore from today we are going to see the power flow analysis. Then we will see in the after s- um, after this class we will study the Gauss-Seidel load flow analysis and then Newton-Raphson load flow analysis. So as I told, we have now have the necessary models to start to develop the power system analysis tools. And the most common power system analysis tool is the power flow, that is also known sometimes as the load flow. And what are the benefits of this power flow and what are the significance of this power flow? Power flow determines the how the power flows in a network, and it is also used to determine all bus voltages and all currents. Because of constant power models, power flow is a nonlinear analysis technique. We will see how this constant power models this power flow becomes nonlinear analysis technique, and this power flow is a steady state analysis tool. As I told you, this power flow is a nonlinear analysis technique, so it's better to know about the linear and nonlinear systems. We know that a function h is called nonlinear if it follows superposition and homogeneity rule. And like here it is this alpha 1 mu 1 plus alpha 2 mu 2. Here alpha we have considered as constant. So this will comes out and h mu 1 plus alpha 2 h mu 2. So if this follows, then we can say that the function h is called linear. That means this output is proportional to the input and the principle of superposition holds. And if we want to see the example of linear and nonlinear systems, then we can see here, suppose a function having uh, it is written like this: hx is equal to cx, and if you do the cx plus 1 plus x2, then it should be cx1 plus cx2. Then here we can see that this superposition and homogeneity follows. So this is called linear system. Now if we want to see the nonlinear system, then suppose the function having cx square. Now suppose if you do x1 plus x2 whole square, then it is not going to be equal to the individual terms. Cx1 square plus cx2 square, this will not equal to this whole term. So here this superposition principle violates. So this is a nonlinear system example. Now, and what are the linear power system elements? The linear power system elements are like resistors, inductors, capacitors, independent voltage sources, and current sources are all the linear circuit elements. And for resistors, this equation we can write V is equal to Ri, and this for inductor we can write V is equal to XLI, and for similarly for capacitor we can write V is equal to 1 divided by j omega Ci. So these are the equations for having voltage and current equation through resistors, inductors, and capacitors, and these are the linear circuit elements. And apart from these, independent voltage sources and current sources are also the linear circuit elements. Now these systems can be maybe analyzed by superposition. As I shown here the example, we can see this is a example of linear system. Here these independent voltage sources are present and the resistors, we know that this is a linear circuit element. So we can apply here superposition principle. If you want to calculate the current through this R3 in first step, you can assume this voltage source V2 as
Sir,
yes.
inductor and capacitors are linear device.
Yeah, linear device.
Okay, sir.
Don't confuse the differential term. Differential term is also a linear term, so that's why b like VL is equal to L diy dt.
Yes, sir. I am confusing with integration and differentiation because of that. This will be uh, linear or not.
Yeah, differentiation integration both does not constitute the linearity. Means both are linear terms.
Okay, sir. Thank you, sir.
So here you can, this is well-known example for linear system. So I think you are able to find this current in R3 by applying this superposition principle, where we assume first we assume the all the s- we assume the first voltage source V1 and short circuit the another voltage source. From there we get current through I3, and in the next step we subsequently we assume this V1 as short circuit and V2 as the power source for this, the current source for this, the from which this resistor is drawing the power from the voltage source V2. So from there we can find the current through R3, and by adding both these we get the final current that is flowing through R3. Now, and suppose now what this in the place of this resistor, now we assume this constant power load. So that becomes the nonlinear system. These constant power loads and generator injections are nonlinear, and hence system with these elements cannot be analyzed by superposition. So that is the thing. In our power systems, we are having constant power loads also, and this generator injections that both constitute the nonlinear elements. Hence, these systems cannot be analyzed by superposition. And these nonlinear problems can be, it is very difficult to solve and usually require an iterative approach. So let us see some of the examples of nonlinear system mathematical example, like this function s square minus 2. It is a nonlinear function, so it has solution of plus minus 1.414. Both solution has solution plus 1.414, that is plus root 2 and minus root 2. And this nonlinear system x square plus 2 has no solution, has no real solution. Here it is seen through these graphs. So we can see that nonlinear system may have solutions or it may not have solution. And this graph of x square minus 2, we can see here it cuts the x-axis at 2 points, so it has two solutions where fx is equal to 0. And here we can see that this x square plus 2 does not cut this x-axis, therefore it has no real solution for this function. Now if we want to see the one of the electrical example, like one of the circuit where we can show that how this is nonlinear system, where we can having multiple solutions. So this is, we assume one load that is constant power load, and the load value is 18 watt, and we have assumed this is resistive load, but anyway this is drawing 18 watt power. So either it have solution or it have multiple solutions. How we can find? So we will simply just find this I. Uh, uh, so it is given that power is equal to 18 watt. So I square R load, and then I we can write is equal to 9 divided by 1 plus R load. We have assumed this as a resistive load. So 9 divided by 1 plus R load, that will I current value. So current value will be 9 divided by 1 ohm plus R load. And this R load we multiply here, that will 18 watt. On solving this will comes So it will be 81 into R load and 18 into 1 plus R load square plus 2 plus 2 into R load. So on solving this, you will find that one value is 2 ohm and another value is 0.5 ohm. So this is the one of the circuit example that shows that how this constant power load behaves as a nonlinear system. That makes the system as a nonlinear system. Till here, any doubt,
Uh,
Neil?
yes, sir.
Yes.
Sir, not only our power systems is non-linear, all the systems are non-linear in practical life.
How it is that? Yeah, in practical life, systems are non-linear, but like biasing is there, always be having biasing in the system. It is not ideal system. So then that's why systems are non-linear. But what you want to say here, Anil?
Sir, I want to say कि linear systems are exist are not in practical life, practical approach.
Resistors is non-linear element. So that is practical system. I am not getting your doubt. Hello.
Yes, sir.
What is the means like you want to say tell some more example of the practical system that is non-linear.
Sir, I want to say our charger is non-linear system because there is capacitor, I mean diode and transistor. They are present.
Yes, so diode is a non-linear element, right? Yeah, you are true that this most of systems are non-linear elements because ideality we don't have in real we not don't see in the we don't see in our real life. Some biasing will be there, some like noises will there. So always whatever if you do the experiment work or whenever you have faced the real system, real physical system, then they are having the non-linearity present, and there may be computational errors, there may be mathematical errors, there are many things like incorporates in the real life system. So that is the nonlinear that constitute the nonlinear system.
Okay, sir.
So now coming to this bus admittance matrix, we have covered many problems in the lecture number 4 on the bus admittance matrix session number 4. But here I just want to show the how this we can derive this bus admittance matrix for a given system. There we have directly see the there we have directly seen the how we can apply the shortcut for finding diagonal non-diagonal elements. But here we will go from the scratch, from the basic one. So the first step in solving the power flow is to create what is known as the bus admittance matrix and often called as Y bus. So bus admittance matrix or by bus written both having the same thing, and this bus Y bus gives the relationship between all the bus current injections I and all the bus voltages V. So this basically we apply this and that correlates this voltage and current, that I denotes the current injections and the V denotes the bus voltage, and this Y bus is developed by applying KCL only at each bus in the system to relate the bus current injections, the bus voltages, and the branch impedance and admittances. So let us see some examples based on the Y bus. So we have to determine the bus admittance matrix for the network shown below, assuming the current injections at each bus having this GI the current injection and DI the current demand. So so I have written down here IGI the current injection into the bus from the generator and IDI the current flowing into the load.
And sir, II is the current at bus.
Yeah, current injection at the bus means
Okay,
like
sir.
like if it is positive, then we are having this generator current injected by the generator is more than the current demand from the load, and if it is negative, that means that shows that it is having it is having more demand at that bus by the load. So this
And sir, if II is zero, then
that I0 means like both injection and demand both are equalizing each other.
it means that whatever the demand of load, we are giving those amount of current.
Yeah, correct. So yes, correct, Anil. Assuming this, this II is the current injection at each bus, and GI denotes the current injection into the bus from the generator, and DI denotes the current flowing into the load. Now we have taken the examples having four buses. This one denotes that is here one generator is connected, and here we can say load 1 is also connected to the bus 1, and here other another load is connected at bus 2, and here another load is connected at bus 3, and at fourth number bus this one more generator is connected. You may write like here G1, G3, and G4, and these are the impedances of the line connecting the buses. So 1 and 2 is connected by this ZA, and this 1 and 3 is connected ZB, and 1 and 3 2 and 3 is connected by ZC, and 2 and 4 is connected by ZD, and there is no connection between first and 4, 3 and 4. So these are there are no lines present between these buses, some buses also. So now we have to, for finding this, as I told, for finding this, for developing the Y bus, we have to apply KCL at each bus so that we can correlate this bus current injections, bus voltages, and branch impedances. Now applying KCL at bus 1. So what is this thing? I is equal to, so this is the IG1 minus ID1. So I have written down here, and this I1, this I1 is also equal to, so whatever is the amount left, so IG1 and this is ID1. So whatever this amount I1 comes, that will equal to I12 plus I1, that is I12, and this is I13. So that will be I12 plus I13. So how you can write I12? I12 becomes, so we can write I1 is equal to I12 plus I13. So I1 what will the value I12 I12 will be we have also assumed this voltages at bus 1 as V1 and at bus 2 V2 and bus 4 V4 and bus 3 as V3. So I12 what is the value of I12 Anil? V1 minus V2 divided by
V1 up, Z1, Z1, ZA,
ZA,
ZA.
ZA, correct. And I3, I13 and I13 will be
Uh, V1 minus V3 divided by ZB.
is correct, very good. So that will be the I1. That is the current injection at bus 1. I1 is the value of current injection at bus 1. So we can directly write I1 either two ways, either by knowing this generator or load current, or either by knowing this voltage and this impedance values of the buses, impedance values of the
Sir,
bus. Yes.
sir, load is present outside the this network. मतलब ZA, ZB, Z3 are load are load 1 or load 3 you return. These are load.
Yeah, that is the demand at that buses, load demand by the buses, load demand at these buses, power demand at these buses.
Okay, sir.
So these are not external, these are connected through these buses, these are connected to this system. So these are having some, like these are having P1 plus JQ1 power demand from this bus, and this load 2 having also P2 plus.
It means that sir, I13 is going from G1 generator. It is also load demand.
IG1.
I13 is going from IG1 generator 1. This is also a load demand current.
That is the power flowing into the power flows into the line, that you can also say that having load demand only. Yeah, correct.
Okay, sir.
Because these are not active element. Active element is the generator only. These are only the passive elements. So I have written down here I1 2 plus I1 3, that the same thing. Now we simplify this, and by using this yj is equal to 1, admittance value is reciprocal of impedance value, so we can write za is ya is equal to 1 divided by za, and yv is equal to 1 divided by zv. So we will get I1 as y1 ya plus yv into v1 minus yv v2 minus yv v3. Similarly, you can find I2, that is I21. So how you can find I2? I2 we have considered that from each buses we have considered that current is flowing out from that bus. So here I have written down I21 and then I23 and then I24. So they are the three lines connected to this bus 2. So I21, I23 and I24. And we have also considered that all the currents are flowing out from that bus, through from that bus to the line. So you will get I2 like this, and we can get similar relationship for bus 3 and 4, and then we can find write this equation. So what are the some conclusions here? By writing this KCL at verse 1, we can see that this directly we can whatever the elements connected to the bus 1, we can directly write the admittance values at the diagonal elements. So y1 plus y2 we can write here, and other element just we take the negative of that value. So we have we seen that bus 1 is connected to bus 2 by this ZA element. So we can here directly write that, sorry, one mistake is there. This one is by a v2. So this is minus ya, and with the bus 3, this will also minus yv.
Sir, at a bus we are assuming all the current is outgoing only.
Yes,
Rather than we assuming current I1 bus 1 to uh, bus 1 to bus 2, but at bus 2 if you writing KVL, KCL, then all the current is outgoing.
yeah, but we are writing right down, we are writing like this. That why we can tell that current injection into the bed that was. So whatever the amount current left, so that will denotes the current injection. So how you can write I2? So we have assumed this I2 as the current, the amount of current injected into that bus. So we have to assume that current flowing from that bus as flowing from that bus. So it is coming from the voltages from the bus. So whatever the convention it will come, it will tell this voltage also, voltage value also. Another thing is that we have assumed this I1, I2, I3, that is the current injection into the bus, the current injection at each busage. So that's why we are following that thing.
Okay, sir.
So remember that we are whatever the we are taking the I1, I2, that is the amount of current injected at each bus. So these are, as I told you, these are the only that demanded from these buses. So we have to take as that is going out from the bus. We cannot take it as like this is injecting the current into that bus. So similarly for I2, so we have all the diagonal, all the elements that are connected to this bus 2. We have taken it as ya plus yc plus yd. This we can see the ya, then yc, and then yd, and all the elements are, and the non-diagonal elements we can take minus ya, minus yc, and minus yd. So here we can see that these diagonal elements, the elements that is connected to each bus, that we directly write down with positive sign only, and this bus for bus 2 similarly, and for bus 3 all the element that is directly connected to that bus, and yd the element that is connected to the bus 4, and all the elements like here, and here is the y12. So how you can write y12? Y12 it written it is the admittance value of the negative of the admittance value of the element that is connected between bus 1 and bus 2, and this is the y13. So it is the negative of the admittance of the line that is connected between the bus 1 and bus 3. And see, this is a symmetric matrix. By bus is a n cross n symmetric matrix. So we can write these values also in just that way. So now we can write down the conclusions that we have drawn by the solving this by bus. Uh, the diagonal terms y, ia are the self-admittance terms, that is equal to the sum of the admittance of all devices incident to bus I. And the off-diagonal limits y, ij are equal to the negative of the sum of the admittance joining the two buses. So diagonal limits we have to directly sum up the admittance of all the lines, and here we are taking the negative of the sum of the admittance joining the two buses. And with large system, bus is a sparse matrix. That is, most entries are zero. We will see some questions on the sparsity, sparsity of line also. So here, since this is a four bus system, so we don't have to so many zero value. Since and if suppose this system is large, so it is not necessary that this bus one is connected to each and every buses. It means nearby buses only need to be connected to the each other. So that's why for large system, this Y bus matrix is generally sparse in nature. Another thing is that some terms such as the byline model only affect the diagonal terms. So this is the most important and is also important for gate point of view. So in gate exam, what they do, they will give you the actual system and having the bus is given, and now they are telling that we are connecting this shunt admittance value and shunt capacitance value at different buses. So what will be the new bus? So in that case, if you directly match with all the off diagonal elements, if off diagonal elements are same, then you can directly choose one option. If other options having different values, and because in that case, in some terms only the diagonal terms are affected. So that's why this point is very very important. And this is the one more example where you can directly solve by without without applying the KCL, without going to the basic one. You can directly apply the how we can find the diagonal elements and how we can find the off diagonal elements. So this is three bus network, and so it is a by bus is a 3 cross 3 matrix, and here this impedance values of line are given, impedance values of the that is connected at which buses is given. So what is the first step? If the impedance value is given, then you have to convert the impedance into admittance. So we have converted this impedance value into admittance. Now for diagonal elements, it is the sum of admittance connected to it. So we have to just add up the admittance value, whatever the connected at each bus is. And for our diagonal elements, we have to take the negative of the admittance between the nodes. So that will be the off diagonal limits. And since y was a sparse matrix, so y12 is equal to y21 and y31 is equal to y13 and y32 is equal to y23. And this is the final we got. And so the first question that is we are now going to see from the gate 2017 set 1. And this problem says that a 3 bus power system is shown in the given figure below, where the diagonal elements of bus matrix are this one and this one. The per unit values of the line reactance PQR shown in the figure are. So how we are going to find this one? So y11 is given, so we can write this the y12 plus y13. We got three equations, so we can get the individual value, that is the admittance of the lines connected between each buses. So now we can correlate with the given values. So P is nothing but 1 divided by 2 3, that is these are PQ are the PQ
Sir, P
are
is impedance.
yeah,
P, Q, and R is impedance. That's why we are taking one by with
yes, correct. So these are the reactances. So we have to again do the reverse. And now the next problem that has been asked in GATE 2021, and in this problem a 3 bus network is shown and the considered generators at ideal voltage sources is, if rows 1, 2 and 3 of the bus matrix correspond to bus 1, 2 and 3 are respectively, then Y bus of the network is. So this is little bit good question. and here you have to go by the conventional way, means here you have to go by the what we have seen by using the KCL. So this is since three buses are given, so 3 cross 3 bus matrix will be formed, and now we will apply KCL at each buses. So we can write I1 as V1 minus Vx divided by J, and R2 as V2 minus Vx by J. Similarly, we can write the I3 value, and after that we will apply the nodal analysis at X so that we can eliminate Vx value. So we will get Vx as V1 plus V2 plus V3 divided 4. Now we put this Vx into I1 so that we will get I1, and similar way without solving. This is since this is a this whole system is like having symmetric in nature, means like whatever the equation we are getting for V1, we are getting for I1, similar type of equation we will get for I2. So
I2 and I3 also.
yeah, correct, Anil. So this way you will get I2 and I3 values. So you will get I1, I2, I3, and finally we get the answer as C. The next question is that I think I have not written down here the year. So this question is that the bus admittance matrix of 3 bus power system is shown below. Considering that there is no shunt inductor connected to any of the buses, which of the following cannot be true? And it is of 2 marks. So in this problem, you have to tell that which of the following is not true. So the first thing is that if you do the summation of any row is that comes at 0, then that means that no shunt element is present at bus. And if you do and if it not coming at 0, then that means that shunt element is present at that bus. So let us solve this problem. So we can write down by 1 2 as minus J10 first, because this J10 is given, and for by 2 3 we can also write, sorry, minus J4, and for by 2 by 1 3 we can write as minus J5. Now we have to find the shunt admittance. So the line charging admittance of line is represented as pi equivalent. Therefore, we can say that since there is no shunt element present at bus 1, because we have done the summation that comes 0, so by 1 0 is equal to 0, and for y2 0, this y2 3 divided by 2 will come, so it will equal to j 0.5 after doing summation of minus j10 minus j4 and j 0.5, that will come as the diagonal elements. So this will be j 0.5, and similarly by 3 0 will be by dash 2 by dash 2 3 divided by 2 plus j 0.5, that is j1. So all the elements we are getting from here, the shunt element value we can directly write from here. This not only gives the shunt element present, but it also gives the value. So this y20 is equal to j 0.5, y3 is equal to j1, we are getting from the matrix only. And since y1 was 0, so there is no shunt element presented that bus. So in that way we can find that what are the shunt elements present at these buses. So we can say that between lines 1 and 2, no line charging susceptance, and between lines 1 and 3, no line charging susceptance, and between lines 2 and 3, line charging susceptance present, and at bus 3, shunt capacitor is also present. So what are the correct options? The first option is that line charging capacitor of finite value is present all the three lines. It is incorrect. Second option is that line charging capacitor of finite value is present in line 2 and 3 only. Yes, this is correct. So we have seen that line charging capacitor is present at 2 and 3 only. So this is correct. And third option is that line charging capacitor finite value is present in line 2, 3 and shunt capacitor of finite value is present in bus 1 only. So this is second statement is correct. After this one says shunt capacitor of finite value is present in bus 1. This is incorrect. So this is also incorrect. And this last option that line charging capacitor of finite value is present in line 2 and 3 only. And shunt capacitor of finite value is also present at bus 3 only. So both are correct. So here it is asking about cannot be true. So A and C are the correct option for this problem. Now let us come to the next part. So in this problem, it is asked that the bus admittance matrix of a power system network is given and then a transmission line connected between bus 1 and 3 which is represented by the circuit shown in the figure. If the transmission line is removed from the service, what is the modified bus admittance matrix? So this is very easy question and it is also of 2 marks. So here we can also say that all the diagonal elements are equal and off diagonal is also same. Therefore, all transmission lines are identical 1, 2, and 3. And one transmission line is given here, so you can directly write all the values and on solving these on removing this line connected with bus 1 and 3, you will get the final answer. Now let us see the sparsity and number of transmission line. So the sparsity is denoted as it is the ratio of it denotes the like number of zero elements in the system. So the how you can find the percentage of sparsity? It is the ratio of number zero elements in bus and to the total number of elements into 100. That denotes the sparsity of matrix. Basically, it denotes that how your transmission lines are like closely zigzag or means like how this they are not connected with each other. So more the sparsity, that means like the less number of lines are connected to each other. And other expression is that how by knowing the sparsity of matrix you can directly find the number of transmission lines. If you want to remember this expression then it is very good, otherwise you can also directly solve by knowing the concept of finding the bus matrix. And here y and any the number of buses or order of matrix. So based on the sparsity of matrix, let us solve by this way. First way where we apply this directly this concept of bus. So the question is that a 1000 cross 1000 bus admittance matrix of an electric power system has 8000 non-zero elements and the minimum number of branches in the system are. So the diagonal elements in bus matrix is always non-zero. It denotes the number of buses in the system. So diagonal elements is 1000 and off diagonal elements can be either 0 or non-zero. Non-zero diagonal elements means 8000 minus 1000. How it comes? It comes from here. It is given that 8000 are non-zero elements. So of non-zero of diagonal elements will be, since 1000 is always non-zero, so it will be 7000 non-zero of diagonal elements. And out of 8000 non-zero elements, 1000 are diagonal elements and 7000 are off diagonal elements. And one transmission line consists of two of diagonal elements. So just you have to divide by 2, you will get 3500 as the answer. Anil, did you get this problem? Anil?
No, sir. Repeat, sir. Can you repeat, sir?
Yes, sure. So the concept is that a bus matrix, a bus matrix, like in this problem you see diagonal elements. Are you agree with that? Diagonal elements is always non-zero.
Yes, sir. Diagonal element is non-zero because
Some lines are always
diagonal.
yeah, some lines are always connected
Yes,
to
sir.
each other. Means one line must be connected to a, a bus. That is 100% sure. That is the necessity.
Yes, sir. If it not connected, then it will go outside the system.
That is go out of service. Correct. So
Yes.
uh, diagonal elements are always non-zero, and the off diagonal elements may be zero or maybe non-zero. That depends. That is connected to different buses or not. Correct. So we have to find the number of off diagonal elements. We have to find the number of non-zero off diagonal elements, and each off diagonal elements, like one transmission line consists of two off diagonal elements. This line is very important. Here, sorry. Here, one transmission line consists of two off diagonal elements, yik, yki. So if you find this
Yes, sir.
number of
Yes.
off diagonal
If
elements,
line 1 is not connected to 3, then 3 is not connected to 1 also.
yeah, correct. So if you find this number of off diagonal elements, number of non-zero off diagonal elements, that means you can find the number of transmission lines. So you have to divide by 2. That denotes the number of transmission lines. Did you get?
Yes, sir.
That is the only thing. First, you have to find the number of non-zero off diagonal elements, and after dividing it by 2, you will get the number of transmission lines. In the like we have seen the first problem. There you can see that here here this like four buses are present in the system. So how many non-zero off diagonal elements should be present? 8, correct. Then see 1, 2, 3, 4, 5, 6, 7, 8, correct. This one, 2, 3, 4, 5, 6, 7, 8. So 7 off diagonal elements are present in this bibus matrix, and if you have to divide by 2 only, so that you will get the number of transmission lines. Now if you don't want to put your mind, then directly go by this approach. This percent number of transmission line, that is n square 1 minus x minus n by 2. First you have to find the sparsity. A sparsity is the number of zero elements in bibus. So this one is the 1000 cross 1000 is the number of elements in the bibus, and 8000 is the number of non-zero elements. So number of non-zero elements is 8000. So number of zero elements we have to subtract from the total elements and divided by total number of elements in the bibus. So you will get 0.992, and on putting this value you will get number of transmission lines. N is the number of bus in the system. So we will get directly 3500. Either way you can remember. Now let us see this general classification of system buses. So generally we classify our power system bus into three types of buses: slack bus, load bus, and generator bus. In slack bus, that is, we take it as either swing bus or infinite bus, and here this magnitude and phase angle of the voltage are specified. It is the specified, and we generally take it as reference, and in per unit we generally assume it as 1 at the angle of 0 per unit. So the voltage magnitude in per unit we take it as 1, and delta we take it as 0. And for the load bus, this is also known as PQ bus, where the real inductive powers are specified, where P and Q are specified. And for voltage control bus, that is also known as PV bus. It is also called as generator bus or regulator bus, and this real power or voltage magnitude are specified. So these buses are given here: bus type, specified quantities, unknown quantities. So select bus, load bus, voltage control bus. What are the specified quantities? And this is very important for further means like for further things be and generally asked in interview, what are the select bus, load bus, and voltage control bus, and what are the specified quantities. Example.
Yet load bus, sir, active power and reactive power are specified quantities.
Yes, in load bus P and Q are specified quantities. How you can define the load? You should know that what are the amount of power they demand. So in questions you also see that this there is load having demand of 10 kVA, having demand of 10 watt, 10 kilowatt, having demand of 10 kVAr plus 10 kilowatt. That is written like that. So that is means that is only that denotes the load bus where the load is connected having
And sir, slack bus.
slack bus we generally take as the like the bigger generator in the system, like the why little bit disturbance in the system we cannot going to change the voltage and angle of the system, like a bigger system that are having enormous amount of power capability to deliver. So by disturbing like you are by disturbing to that bus you cannot going to change the voltage that is being supplied by the generator. So here this voltage and angle is specified, and we take it as the reference. And after taking this reference of select bus, we are going to find the other bus voltage and angle, because we have known this voltage only, the select bus voltage, and we are also known this voltage control, this PV bus where the generator is connected. Select bus is also where the generator is connected, but the bigger in size generator where it is connected to that bus is considered the select bus, and it is also called as swing bus or infinite bus, right?
Okay, sir.
So this problem is also easier, and here all the things having like you have to find the properties of bus 1, bus 2, and bus 3, what are types of the buses. So here three buses are given, and in the we can see that at bus 2 this P and Q are specified. Anyway here this alternator is connected, that in the not you cannot say that this is a PV bus. So the P and Q are specified, so we have to take it as PQ bus. And for bus 3, this is infinite bus, select bus. It is already given, and it is given with voltage and angle magnitude. So we have to take it as in select bus. So bus 3 we have taken select bus, and for bus 2 what are the things given? It is given the V magnitude. So sorry, for bus 1 it is given as V magnitude, and this how this P is given. P is given by the angle. Here you can see this angle is having the phase shift by pi by 2 with respect to voltage. Voltage angle is theta 1, and this angle this
Means the slack bus. Bus one is slack bus because angle and voltage are given, are specified.
angle where angle is given in bus 1. Angle is theta 1, but theta 1 value is not given. It should be a defined value. It should not be variable. So it is not slack bus. Voltage magnitude given 1.05. That is okay. But theta 1 is not given. And other thing is given that theta 1 this voltage magnitude and current injected into this bus, the phase difference between voltage and current is pi by 2. If phase difference in voltage and current is pi by 2, that means reactive power is 0. Sorry, active power is 0. Only reactive power is being is being injected into that bus. So active power injected by this current source is 0. So therefore P is specified also, V is also specified. So it is PV bus. Bus 1 is PV bus. Correct, Anil?
Okay, sir.
Now this is my last question, and that is asked in GATE 117 set 2. And here we will see this in Newton Raphson. So this in today is session 16. So we will see in session 18 Newton Raphson. And in next class we will see Gauss seidel load flow method. So right now just I want to say that if you they are asking about size Jacobian matrix, you have to directly apply this expression 2 into PQ bus plus PV bus, and you have to find the PV bus and PQ bus. Here PV bus is directly given, there is 20 PV buses appear in the system, and you have to find the PQ bus, and the size of Jacobian matrix is also given. So PQ bus is coming as 40, and then you can find the total number of buses in system that is asked in this question. So total number of buses will be PQ bus plus PU bus and one is the slack bus. So 61 is the correct answer for this problem. So that's all. Thank you for attending this session, and we will meet in the next
Thank you,
session.
sir. Thank you, sir.
Thank you, Neil. Okay, bye bye.
Bye, sir.